Today we're going to be talking about transformations and similar figures. So let's take a look at your notes page and please write down what I write down. First thing I want to do is go over some of the vocabulary words with you. So remember that a dilation is changing the size of a figure. Scale factor is the number multiplied by to dilate a figure. Similar figures are the same shape but a different size. So today we're going to be determining if figures are similar. And we can determine if two figures are similar if the second one can be attained from the first by a sequence of transformations and dilations. And you have to do a dilation in order for a figure to be similar. So we're going to try to prove that a dilation was done to these figures. Let's take a look at the first example here. We've got triangle DEF and triangle GHI. These triangles are turned the same way. So the first thing we want to do is get the figures on top of each other by translating. And we can translate DEF 5 units to the right and 2 units down, and it will land on top of GHI. When we do that, angle D will land right on top of angle G. Angle F will be here, and angle E will be here. So that's going to be our new triangle. Now, the next thing that we're going to do to figure out if these triangles are really similar to each other is we're going to write ratios comparing the lengths of their sides. So we're just going to count how big their corresponding sides are. Remember corresponding sides from our work with congruent figures yesterday. So we've got corresponding sides. I've got HG would correspond to ED, and then GI would correspond to DF, and then IH would correspond to FE. Well, if I count how big HG is 8 blocks or 8 units, and ED is 4 blocks or 4 units. So I just write a ratio or a fraction, 8 over 4, and that reduces to 2 over 1. Then I do the same thing with the other sides. Now since I started with a side on the bigger triangle first, I've got to do the same thing this second time. So I've got to start with the side that's on the bigger triangle. So GI, if I count how many blocks that is, that's 6 blocks. And then DF is 3 blocks. So 6 over 3 also reduces to 2 over 1. Then I could do the same thing with IH and FE, but I can't count how big IH is because it's a diagonal line. I would have to use the Pythagorean theorem to figure that out. So I really wouldn't worry about that side. As long as you do two out of 3 sides on a triangle, then you can stop there. You don't have to do the third side. So both of these proportions are equal to each other. Both of them were 2 over 1 when we reduced it. So since the ratios are equal to each other, triangle HGI is dilated of EDF. So the two triangles are similar because we could do a translation and a dilation and actually get those triangles to be exactly on top of each other. So if we look at example number 2, we've got 2 rectangles here, and if you notice on these two, we've got one rectangle that's laying on its side and another rectangle that's kind of vertical. So the first thing we've got to do is rotate that smaller rectangle 90 degrees so that we can make those two rectangles the same direction, the same orientation is what they call that. And then, after we've done that, then we can just count our side measurements and set up ratios to see if the ratios are equal. So WT on the smaller rectangle would correspond with XY on the larger rectangle. And WT is 5 units and XY is 7 units. So I would write the ratio 5/7. TU on the smaller rectangle is 3 units, and it corresponds to YZ on the larger rectangle, which is 4 units. So I can write that ratio 3/4. Now you could write the other two, but you can probably already tell that 5/7 does not equal 3/4. So these two rectangles are not similar. Now if you're not sure if those two fractions are equal to each other, you could divide both of them and see what their decimals are, or you could cross multiply. 5 times 4 is 20, 3 times 7 is 21, and those don't equal each other. So these ratios are not equal, so therefore the two rectangles are not similar, and a dilation did not occur. Now if you want to, right here, you could try A and B on your own and pause the video, and then I'll show you how to do it. So if you want to try them on your own at this point, pause the video, and then I'm going to go ahead and show you how to do these two. So if we look at example A, it looks like I'm going to have to flip the triangle over so that those two triangles are the same direction. So if I flip triangle STU over a vertical line that I've drawn between those two triangles, then S is going to land right here. T is going to land right on top of Q. And then U is going to land here. So there's my new triangle. And now remember, I want to set up ratios of my side measurements. So if I start with my smaller triangle, side ST would be similar to PQ. If I count how big ST is, it's 3 units. And if I count how big PQ is, it's 6 units. And that reduces to 1/2. Now I can't do the diagonal side without doing the Pythagorean theorem, so I'm going to skip that side, but I'm going to do the bottom side of each triangle. So since I started with the smaller triangle, I've got to start with the smaller triangle again. TU, we're going to see if it's similar to QR. Well, TU is 5 blocks, and QR is 10 blocks, and that also reduces to 1/2. So since both of these ratios are 1/2, that means they're equal ratios, which means that these triangles are similar. And we proved that by doing a reflection, and then of course it was a dilation. If they're similar, then obviously we did dilate the figure. If PQR is the original, then we dilated it by 1/2. The scale factor would be 1/2 to get STU. If STU is the original, then we dilated it by a scale factor of 2 to get PQR. Now, let's look at example B. So on this example, the trapezoids are turned the same way, so we won't need to reflect or rotate those. All we'll have to do is translate EFGH on top of A, B, C, D, and we can translate it to the left and down so that it's on top of the other trapezoid. And when I do that, I'm going to line up H with D, and that means E would be here, one block below A, and then F would be right there, and then G would be right here. So there's my trapezoid after I've translated it. And now I'm going to set up ratios of my side measurements to see if these side measurements have the same ratio. So let's start with our smaller triangle, and let's put EH over top of AD. And EH, its side measurement is 4 units, and AD's side measurement is 5 units. And that doesn't reduce. Now let's put HG over top of DC. HG is 4 units, and DC is 5 units. So right now it looks like our ratios are the same. Let's do the third side, not the diagonal side. I can't do that one without using the Pythagorean theorem, so I don't want to go to that much trouble. But I'm going to go ahead and try EF and put it over our larger triangle, and that side would be AB. And if I count, EF is 2 units and AB is 3 units. So the question is, does 2/3 equal 4/5? Well, 2/3 as a decimal is 0.6 repeating, and 4/5 as a decimal is 0.8. So they're not equal to each other. Again, you could have set up a proportion 4/5 and see if it equals 2/3. Cross multiply 4 times 3 is 12, 2 times 5 is 10, and they don't equal each other. So this is not similar. So that means that we did not dilate EFGH to make ABCD, because those two trapezoids were not similar. Okay, on this last example here, we've got Ken that's got a photo of a Dalmatian, and he's going to enlarge that photo by a scale factor of 2 to put that picture on his web page. Then he takes the web page photo and enlarges it by a scale factor of 1.5 to print it. If the original photo is 2 inches by 3 inches, what are the dimensions of the print? Well, the first thing we're going to have to do is take the original photo and multiply it by the scale factor of 2 to figure out the dimensions of the web page photo. So I take the dimensions of the original photo, 2 inches and 3 inches, and multiply them both by 2. So when I do that, I get 4 inches by 6 inches is how big the web page photo will be. So then I'm going to take the web page photo 4 by 6 and multiply it by the scale factor of 1.5 to figure out what the dimensions are of the print. So 4 inches times 1.5 is 6 inches, and then 6 inches by 1.5 is 9 inches. So the printed photo is 6 by 9 inches. And definitely all of those photos are similar to each other, since they told us in the problem that they did a dilation twice to make the enlargement. So at this point, what I'd like for you to do is to do this guided practice on the back of your notes page, number 1, 2, and 3. And then I would like for you to raise your hand and let me check it and see if you have that correct before you do your homework. Then you can answer number 4 on how confident you are about similar figures after I've checked 1, 2, and 3.